In the winter of 1891, in a water-damaged storage room beneath the Imperial Academy of Sciences in St. Petersburg, an archivist named Pavel Volkov was cataloging architectural drawings confiscated from a monastery in Kazan when he found something that contradicted every engineering manual he had consulted. The blueprint, dated 1782 and drawn in fading ink on heavy linen paper, showed the cross-section of a cathedral dome, not the familiar wooden frame covered in copper sheeting that architectural texts described, but something far more complex. The dome's copper shell was divided into geometric segments, each isolated from the others by narrow gaps filled with what the notation called atmospheric separators. Vertical copper rods descended from the dome's apex through the building's interior, terminating in the foundation at points marked earth contact, insulated junction. The drawing's margin contained calculations in a cramped hand, frequencies, capacitance values, voltage measurements. At the bottom, in different ink, someone had written Функция не декоративная, function not decorative. Volkov photographed the blueprint with the Academy's new camera equipment, noting in his catalog that the design seemed to describe an electrical system. This observation was peculiar because the blueprint predated widespread electrical engineering by nearly a century. The monastery from which it came had been closed in 1887, its archives seized during government secularization efforts. According to the acquisition record, the drawings had been stored in a locked iron cabinet marked Stроительные секреты construction secrets. The cabinet's key, Volkov was told, had been lost during transport. They had used bolt cutters. The photograph Volkov made that day survives in the Academy's digital archive, catalogued under Ecclesiastical Architecture, Historical Interest Only. The original blueprint disappeared sometime between 1917 and 1922, during the chaos of revolution and civil war. Volkov himself left no further notes about the discovery. His catalog entry is brief. Dome section with unusual electrical annotations. Probable error in drafting or later addition by unknown hand. The photograph shows the blueprint clearly: the segmented copper, the descending rods, the foundation connections, the marginal calculations. But the image has never been analyzed in technical detail. It remains filed as an architectural curiosity, timed with 500s, a decorative drawing that someone, for unknown reasons, covered with nonsensical electrical notations. Yet across the former territories of the Russian Empire and the Ottoman domains, cathedrals and mosques constructed between 1650 and 1890 show a consistent pattern. Their domes are copper, divided into geometric segments separated by narrow gaps. The gaps are filled with material that resists electrical conduction: ceramic, glass, certain types of stone. Copper rods descend from the dome's interior structure through the building, often concealed within walls or pillars. These rods terminate in the foundation at points where they contact large metal plates buried in the earth. The plates, when excavated during renovation work, are frequently found surrounded by materials that conduct electricity efficiently when moist clay mixed with charcoal, beds of metallic ore, deposits of mineral salts. Official architectural histories describe these features as decorative elements or structural supports. The segmented copper domes are explained as a technique to manage thermal expansion. The descending rods are identified as lightning protection, similar to the systems Benjamin Franklin developed. The buried foundation plates are classified as drainage features or structural footings. Each element has an official explanation. Yet when examined together, the components form something that resembles, with uncomfortable precision, an atmospheric electrical collection system. On the morning of March 14, 1878, in Constantinople, a British engineer named Thomas Whitmore was supervising repairs to the dome of the Yeni Mosque when he noticed something that his training insisted should not function. The mosque, completed in 1665, had a copper dome divided into 12 sections, each separated from the others by strips of glazed ceramic barely 2 centimeters wide. During the previous night's thunderstorm, Whitmore had observed arcs of pale blue light dancing between the dome segments. His assistant, a local craftsman named Mehmet, told him this was normal. The money breathes with the sky during storms. Whitmore, skeptical, decided to measure. Using a galvanometer borrowed from the British Embassy, Whitmore tested the electrical potential between adjacent dome segments. On a clear day, he measured approximately 60 volts. When clouds gathered, the voltage increased sometimes to several hundred volts. Time, 50s, though never high enough to produce visible discharge. The copper rods descending from the dome, which Whitmore had assumed were purely structural, showed continuous electrical activity. Current flowed down the rods whenever the atmospheric electrical field increased during storms, certainly, but also during fogs, heavy overcast, even on humid days with no visible weather disturbance. The current was small, measured in milliamperes, but it was steady and predictable. The foundation plates, when Whitmore examined them during renovation work in the mosque's crypt, were positioned in beds of damp clay mixed with crushed charcoal, a substance that, Whitmore knew, conducted electricity far better than dry soil. Whitmore documented his findings in a letter to the Royal Society, dated April 1878. He proposed that the mosque's dome might function as an atmospheric electrical collector, a device that accumulated charge from the natural electrical field between earth and sky, then conducted it to the foundation where it dissipated harmlessly. The suggestion was not unprecedented. Atmospheric electricity had been studied since Franklin's experiments, and various inventors had proposed systems to harness it. What made Whitmore's observation significant was that the Yeni Mosque had been designed 2 centuries before electrical engineering existed as a formal discipline. If the dome was intentionally collecting atmospheric charge, its builders must have understood electrical principles that European science would not formalize until the 1800s. The Royal Society thanked Whitmore for his letter and filed it without further comment. No investigation followed. When researchers searching the Society's archives for references to atmospheric electricity rediscovered the letter in 1967, it was noted as an interesting historical anecdote, but not pursued. Whitmore's measurements, however, were precise enough that modern engineers can verify them. The dome configuration he described, copper segments isolated by ceramic, rods descending to foundation plates buried in conductive material, is essentially a capacitor array connected to a grounding system. It would accumulate charge during periods of atmospheric electrical activity and discharge it to Earth. The system would not generate large amounts of power by modern standards, but it would produce steady, low-level current whenever atmospheric conditions were favorable. By the mid-1800s, across Europe and the Ottoman territories, hundreds of buildings featured copper domes with similar geometric divisions. In St. Petersburg, the Cathedral of Saints Peter and Paul had a dome divided into 8 segments. In Vienna, the Karlskirche featured a copper dome with 12 sections separated by narrow bands of lead. In Istanbul, the Süleymaniye Mosque's central dome was divided into 16 segments with ceramic separators. Each building's construction records, when they survived, contained vague references to atmospheric protection or heaven's blessing phrases that architectural historians interpreted as religious symbolism. The segmented design was usually attributed to thermal management or aesthetic preference. The copper rods were classified as lightning protection. The buried foundation plates were described as structural footings or drainage elements. Yet certain details resist these explanations. The ceramic or glass separators between dome segments serve no thermal purpose. Metal expands uniformly, whether segmented or not. The copper rods descend through the building's interior in patterns that correspond to no known structural requirement. They often avoid load-bearing elements entirely, running instead through decorative columns or concealed passages. The foundation plates are positioned in locations determined not by structural load, but by access to moisture near wells, cisterns, natural springs, underground streams. Drainage systems would be designed to move water away from foundations. These plates are surrounded by materials that retain moisture and conduct electricity efficiently when wet. In the spring of 1923, in Moscow, a young engineer named Konstantin Tsiolkovsky was reviewing technical specifications for proposed renovations to the Cathedral of Christ the Savior when he made a connection that would trouble him for years. The cathedral, consecrated in 1883, had a copper dome divided into 12 segments separated by ceramic strips. The renovation plans called for replacing the ceramic with rubber gaskets, a modern material better suited to waterproofing. Tsiolkovsky, whose primary work focused on rocketry and space exploration, had recently been studying atmospheric electricity as a potential power source for theoretical spacecraft. He recognized the cathedral's dome configuration as identical to experimental atmospheric collectors being developed by inventors in Europe and America. Tsiolkovsky calculated the dome's potential electrical output based on its surface area, segment configuration, and the known atmospheric electrical field strength. Under typical conditions, he estimated the dome could collect several hundred watts, enough to power the cathedral's gas lamps if converted efficiently. During thunderstorms, the output might reach several kilowatts. The calculation was theoretical, but the physical principles were sound. The dome was functioning, whether intentionally or not, as an atmospheric electrical collector. He drafted a memorandum suggesting that the cathedral's electrical properties be studied before the renovation proceeded. The memorandum was forwarded through bureaucratic channels and eventually reached the State Electrification Commission, which was at that time overseeing Lenin's ambitious plan to electrify the entire Soviet Union. The commission's response, dated June 1923, acknowledged Tsiolkovsky's calculations, but noted that atmospheric electrical collection was impractical for serious power generation, and that the cathedral's dome modifications should proceed as planned. The ceramic separators were replaced with rubber. The copper rods, which Tsiolkovsky had identified as possible conductors, were removed during structural modernization. The cathedral itself was demolished in 1931, its copper dome melted for industrial use. Tsiolkovsky never publicly pursued the atmospheric electricity question. His papers, preserved after his death in 1935, contain scattered notes about ancient electrical collection, his time lasted 50 mams, and pre-industrial atmospheric systems, but these fragments were never developed into formal research. The memorandum to the Electrification Commission survives in Soviet state archives, catalogued under Rejected Technical Proposals, Religious Construction. On November 8, 1889, in Prague, during restoration work on the St. Vitus Cathedral, workers discovered a sealed chamber within the dome's structure. The chamber, roughly 2 meters square, was accessible only through a narrow passage from the bell tower. Inside lay copper coils, ceramic insulators, and what appeared to be primitive capacitors, glass jars lined with metal foil. A notebook, bound in cracked leather, contained diagrams and notes in Czech and Latin. The diagrams showed the copper dome divided into segments, with coils positioned to capture electromagnetic fields generated when atmospheric electricity flowed through the dome structure. The capacitors were arranged to store the collected energy. The notebook's author, identified by initials J.K., described experiments conducted between 1862 and 1867, sheets measuring voltage output, attempts to store charge, calculations of power available during different weather conditions. The cathedral's chief architect, examining the discovery, declared it the work of an amateur experimenter who had gained unauthorized access to the dome and conducted private electrical experiments. The chamber was photographed, its contents removed, and the space sealed with brick. The copper coils and capacitors were catalogued as historical electrical equipment, amateur manufacture, and placed in the Cathedral Museum's storage. The notebook was filed in the cathedral archives without translation or analysis. When a Czech historian researching 19th century electrical experimentation requested access to the materials in 1978, he was informed that the items had been lost during World War II evacuations. The photographs survive, showing the chamber clearly. The coils, the capacitors, the careful arrangement suggesting systematic experimentation rather than random collection. But the physical objects are gone. The notebook has never been relocated. Yet the pattern of J.K.'s work matches Whitmore's observations in Constantinople and prefigures Tsiolkovsky's calculations in Moscow. All three men, working independently across decades and continents, identified the same phenomenon. Copper domes divided into isolated segments, when properly configured and grounded, function as atmospheric electrical collectors. The output is modest, by modern standards watts or kilowatts rather than megawatts. But in the pre-industrial era, even modest electrical power would have been significant. A few hundred watts could light a large building with carbon arc lamps. A kilowatt during a thunderstorm could drive small motors, charge battery banks, or power electromagnetic apparatus. The question becomes, did the builders of these structures understand what they were creating? Or were the electrical properties an accidental consequence of designs chosen for aesthetic or religious reasons? In the autumn of 1994, in Kazan, during renovations to the Kol Sharif Mosque, a reconstruction of the original destroyed in 1552, engineers discovered something unexpected in the foundation excavations. At precise geometric points beneath where the mosque's minarets would stand, they found copper plates approximately 1 meter square, buried at depths of 3 to 4 meters. The plates were oxidized green but structurally intact, embedded in beds of clay mixed with charcoal and iron filings. Each plate was connected by a thick copper cable to a central junction point beneath where the main dome would be positioned. The cables were insulated with ceramic tubes and sealed with mineral pitch. The excavation director, unsure how to classify the find, consulted with the Russian Academy of Sciences. A geological survey determined the plates dated to the early 17th century, consistent with construction of buildings that had occupied the site before the mosque's destruction. An electrical engineer examining the configuration noted that the plates formed a grounding array, optimally positioned to dissipate electrical current from a central source. The pattern matched modern lightning protection systems. Though the scale was unusual, the cables were thicker than necessary for lightning rods, and the plates were positioned based on geometric rather than structural logic. A decision was made to preserve the plates in place during the new mosque's construction. Times 600s, the copper cables were left intact, though not connected to the modern building's electrical systems. The plates remained beneath the Kol Sharif Mosque, their purpose officially classified as historical lightning protection. Yet their configuration suggests something more deliberate. Lightning rods protect structures by providing a single path for discharge. These plates formed a network, positioned to collect and distribute current from multiple points. The thick cables and large buried plates indicate a system designed to handle continuous low-level current, rather than occasional high-voltage strikes. By the early 20th century, as electrical grids expanded across Europe and the Americas, the copper domes of older buildings were often replaced or modified. The segmented designs were seen as outdated, the ceramic separators prone to water damage, the copper itself valuable for industrial purposes. The descending rods were removed during modernization, the foundation plates buried and forgotten. Buildings that had functioned, perhaps for centuries, as atmospheric electrical collectors were transformed into passive structures, their original purpose obscured by renovations designed to meet modern codes. On the afternoon of February 22, 2011, in Istanbul, a graduate student in architectural engineering named Ayşe Karahan was studying thermal properties of historical buildings when she noticed something anomalous in infrared photographs of the Süleymaniye Mosque. During thunderstorms, the copper dome's surface temperature distributed unevenly. The segments showed different temperatures despite being made of the same material. More significantly, the temperature patterns corresponded to electrical activity. Segments closest to lightning strikes showed brief temperature spikes, but the heat dissipated quickly, flowing down the vertical seams where ceramic separators divided the copper sections. Karahan, curious, examined the building's historical records and discovered references to copper rods, beim 315, that had once descended from the dome's interior but were removed during 1970s renovations. She calculated that the original system, if the rods had been connected to foundation plates, would have formed an efficient electrical dissipation network. The segmented dome would distribute atmospheric charge across multiple isolated conductors. The ceramic separators would prevent uncontrolled current flow between segments. The descending rods would channel collected charge to the foundation, where plates buried in conductive material would dissipate it into the earth. The system would protect the building from lightning, while potentially collecting usable current during electrical storms. Karahan submitted her findings as a thesis project, suggesting that Ottoman builders had developed sophisticated atmospheric electrical systems long before European scientists formalized the principles. Her academic advisor praised the thermal analysis, but recommended toning down speculation about electrical collection. The historical record, he noted, shows no evidence that Ottoman builders understood electrical principles. The thesis was approved with the suggestion that the electrical elements be described as coincidental rather than intentional. Karahan graduated and moved into commercial architectural work. Her thesis, filed in the university library, is occasionally cited in discussions of historical thermal management, but not in electrical engineering literature. Yet the physics remains regardless of intention. a copper dome divided into segments, connected to grounding rods that terminate at buried plates in conductive material, will collect atmospheric electricity. The system functions whether its builders understood electrical theory or discovered the principles empirically through observation and experimentation. The persistent pattern, the same configuration appearing across different cultures, continents, and centuries, suggests either a shared technical tradition or independent discovery of natural phenomena, time 400s, that produce predictable results. In a technical manual discovered in 2003 among documents archived at the Topkapi Palace Museum, an Ottoman engineer whose name is recorded only as Mehmet Efendi described, in 1721, the proper construction of mosque domes. The text specified that copper segments be divided by non-conducting stone and that rods of pure copper descend from the dome's peak to plates of metal buried where earth is moist. The purpose, Mehmet Efendi wrote, was to allow the breath of heaven to flow through the building and return to earth, maintaining balance. Historians who have examined this text interpret breath of heaven as metaphorical language for ventilation or symbolic religious meaning. Yet the technical specifications, copper segmented by insulators, rods descending to buried plates in moist earth, describe exactly the configuration that Whitmore measured, that Tsiolkovsky calculated, that Karahan photographed with infrared. The manual includes a diagram showing how to measure the strength of heaven's breath using a simple instrument, two metal plates separated by a gap, connected to a copper wire suspended from the dome. When heaven's breath is strong, Mehmet Efendi explained, the wire will deflect toward one plate or the other. This is, essentially, a description of an electroscope, a device used to detect electrical charge. The manual suggests testing the dome's installation by observing the wire during storms. If properly constructed, the wire should deflect steadily, indicating current flow. If the wire sparks or produces erratic motion, the segments are not properly isolated, and the ceramic separators must be adjusted. This is not metaphorical language. This is technical instruction for testing an electrical system. Yet because the manual predates formal electrical theory, because the terminology uses breath rather than current, and heaven rather than atmosphere, the text is read as religious symbolism rather than engineering documentation. On June 14, 1967, in Belgrade, during a conference on historical architecture, an electrical engineer named Peter Jovanovich presented a paper analyzing the copper domes of Serbian Orthodox churches. Jovanovich had measured the electrical properties of 12 churches built between 1650 and 1850. All showed similar characteristics: segmented copper domes, ceramic or glass separators, buried foundation plates positioned near water sources. Jovanovich had installed monitoring equipment on 2 churches, recording electrical activity over 6 months. The domes produced measurable current during thunderstorms, fog, heavy overcast, and periods of high humidity. The output was modest, typically 50 to 200 watts during normal weather, sometimes exceeding a kilowatt during storms. But the power was continuous during active weather conditions and entirely passive. The system required no fuel, moving parts, or maintenance beyond keeping the copper clean and the separators intact. Jovanovich proposed that medieval builders had developed atmospheric electrical collection as a practical power source for churches, enough electricity to illuminate icon lamps, ring bells electromagnetically, or charge primitive battery systems. His paper included historical references to churches where lamps burned without oil and bells rang by heaven's command, phenomena that official ecclesiastical histories attributed to miracles, but that might, Jovanovich suggested, have been early electrical systems powered by atmospheric collection. The response to Jovanovich's presentation was polite but dismissive. Several historians noted that medieval builders lacked understanding of electricity. An engineer pointed out that 200 watts was insufficient for practical use. Consensus was that any electrical activity in the domes was coincidental, a byproduct of materials chosen for aesthetic or structural reasons. Jovanovich's paper was published in the conference proceedings, where it has been cited twice, once in a survey of historical building materials, once in a study of atmospheric electricity. His measurements were never disputed. His interpretation was never accepted. The measurements stand in archives, recorded and ignored, across Europe, the Middle East, and parts of Asia, Hundreds of buildings constructed between 1600 and 1900 feature copper domes, with segmented designs, ceramic, or glass separators, copper rods descending through interior spaces, and foundation plates buried in conductive materials. Modern explanations classify these features as decorative elements, thermal management, lightning protection, structural support. Each individual component has a conventional interpretation. When examined as a system, the components describe an atmospheric electrical collector. In the winter of 2019, in a renovated loft apartment in Berlin, a sensor engineer named Klaus Hoffman installed a small copper dome on his building's roof. The dome was divided into 8 segments, separated by ceramic strips, connected by copper wires to a grounding rod. Hoffman had been researching historical atmospheric electrical collection after reading Jovanovich's 1967 paper. He wanted to test whether the system would produce measurable power. Over 18 months, Hoffman recorded the dome's electrical output. During clear weather, the system produced 10 to 30 watts. During overcast conditions or fog, output increased to 50 to 100 watts. During thunderstorms, the dome briefly generated up to 800 watts before the current exceeded the capacity of Hoffman's collection equipment and dissipated to ground. Hoffman published his results on a personal website, along with construction diagrams and photographs. The data showed that atmospheric electrical collection using historical dome designs was functional and measurable. Several engineers contacted Hoffman, expressing interest. A renewable energy company inquired about scaling the system. Then, in early 2021, Hoffman's website went offline. Attempts to contact him received no response. The domain name was allowed to lapse. Archived copies of the site preserve his data and diagrams, but Hoffman himself seems to have withdrawn from public discussion of the project. Today, several firms market atmospheric energy collectors using principles similar to those Hoffman tested. Copper conductors with segmented designs, ceramic insulators, grounding systems. These devices are sold for remote locations where grid electricity is unavailable. Manufacturers describe the technology as innovative, recently developed. Marketing materials make no reference to historical atmospheric collectors, to segmented copper domes, to Ottoman engineering manuals or Serbian Orthodox churches with foundation plates buried in moist earth. The systems function identically to what Whitmore measured in 1878, what Tsiolkovsky calculated in 1923, what Jovanovich documented in 1967, what Hoffman tested in 2019. But the historical lineage is not acknowledged. The technology is presented as new, without precedent, unconnected to the copper dome buildings that functioned for centuries before electrical grids made them obsolete. If history is written by those who control infrastructure, by those who define what constitutes legitimate knowledge, then atmospheric electrical collection was never formally invented because it was never formally forgotten. It existed in practice, embedded in architecture, passed through craft traditions as construction technique rather than electrical theory. When modern electrical grids rendered it unnecessary, the systems were dismantled during renovations. Their purpose reclassified as decorative or symbolic. The buildings remain, copper domes catching sunlight, ceramic separators visible to anyone who looks closely, foundations concealing plates that once grounded current collected from the air itself. The evidence persists, preserved in stone and metal, waiting in archives, documented by engineers whose observations were acknowledged but never pursued. The power flows still, whether measured or ignored, through structures that remember what history has chosen to forget.